Welcome, everyone. In this video lecture, I'd like to give you a short introduction to the global model-specific interpretation method called forest-guided clustering, which can be used to interpret random forest models. The idea behind forest-guided clustering is that we explain the decision-making process of a random forest model by grouping the data into subgroup of instances that follow similar decision paths in the random forest model. But what does that mean? Well, here's an overview on the forest-guided clustering algorithm. Let's start off with the user input. The user has to input a dataset which consists of target values and a feature matrix and a trained random forest model. In the first step, we use the structure of the random forest model to define a similarity between data points. But how is the similarity defined? Well, we calculate the co-occurrences of two data points in the leaves of the different decision trees. As you might know, a random forest model consists of multiple of those decision trees. If two data points now fall in the same leaves of a decision tree, it means that they follow the same decision path throughout that tree. If they do that very often throughout the whole random forest model, it means that they somehow have the same decision rules that define those data points. This information is stored in a proximity matrix. High values in a proximity matrix mean that 2 points are very similar, whereas low values in a proximity matrix means that they almost never fall in the two leaves of a decision tree, meaning they follow very different decision rules throughout the decision trees. This proximity matrix is now used to calculate a distance matrix, which is used as input for k-medoids clustering. As you might know, similar to k-means clustering, k-medoids clustering requires a predefinition of k, which is the number of clusters. In our algorithm, we defined an optimization scheme which optimizes the number of clusters k based on the bias and the variance of the clustering. The bias is defined by the target values, which means we want to have very pure clusters, meaning only, for instance, in the classification problem, only instances of the same class should fall into the same cluster. So the clusters should not be mixed with class instances. And the variance, on the other hand, we can define by the stability of the clustering. So in our case, we take the Jaccard index, which measures the stability of a single clustering, and we use a threshold to remove clusterings which are very unstable. Hence, they lead to very different results if we have little changes in the dataset. Once we have that clustering, we can compute different output metrics. First of all, we have a global and a local feature importance. This feature importance identifies features that show different and concise value distributions across clusters, and thereby I defined either globally important or locally important, meaning important to one of the single clusters. In addition to the global and local feature importance, we also provide the visualization of the decision-making process of the random forest model. This is visualized in a distribution plot and a heat map. I now would like to show you how you can interpret the results of a forest-guided clustering analysis based on the iris plants dataset. This dataset consists of multiple numerical features and a categorical target variable, which are the 3 iris species. A random forest model was trained on the iris dataset, and forest-guided clustering was applied. Forest-guided clustering offers different plots in order to do interpretation of the random forest model. We will start off with the global feature importance plot. This global feature importance indicates which features contribute to the decision-making process of the random forest model. The global feature importance is based on the significance of the differences between cluster-wise feature distributions. So which features show actually different distributions across the different clusters that were identified by forest-guided clustering. That is a major difference between forest-guided clustering and other interpretation techniques, which often rely on the change of model accuracy or model performance. One big advantage of forest-guided clustering is that it does not assume feature independence. So even if you have high correlation amongst features in your dataset, it doesn't affect the feature importance measure. In addition to the global feature importance, forest-guided clustering also provides a local feature importance. This local feature importance reveals the importance of different features for the different clusters. So for instance, the sepal width seems to have a lower importance for cluster 0 than for cluster 1 and for cluster 2. The local feature importance is based on the significance of differences between the feature values attributed to a cluster versus the feature distributions of the whole dataset. So do I see a significant change in feature distribution when I consider a certain cluster compared to the whole background distribution of the feature? This is also a major advantage of forest Geiger clustering, because the local feature importance allows to understand the relevance of each feature for a specific cluster. Last but not least, forest Geiger clustering also helps us to get an understanding of the decision-making process of a random forest model. Therefore, you can use the decision path plots. They consist of a heat map and a distribution plot per feature. Let's start off with the heat map. The heat map provides a general overview on the target value attribution and feature enrichment or depletion per cluster. But what does that mean? Coming back to our iris example dataset, you can see that our algorithm optimized the number of clusters and returned an optimal number of clusters, which is 3. You can also see that the target value attribution to those clusters is almost perfect. However, we have some data points which are misclassified here. These data points can be used to inspect your dataset further and see if some of your data points were, for instance, mislabeled or are extreme outliers. Coming to the distribution plot. The distribution plot can be used to get an idea of the distribution of feature values within each cluster. Combining those two plots, we can actually derive the decision rules that were made in the random forest model. Just to give you an example, the first cluster is mainly defined by target 0 values, so target values of class 0. So we can now go there and see that class 0 seems to be defined by a low petal width, a low petal length, a low sepal length, and a high sepal width. We can do the same for each of the target values, so for each of the classes, and thereby derive decision rules for each of the classes that we have in our dataset. To summarize, the major advantage of forest Geiger clustering is that it allows us to look inside the decision-making process of a random forest model, and thereby helps to uncover distinct feature patterns that define different subgroups of instances in our dataset. The major drawback of forest Geiger clustering is that it's limited to random forest models. So you can only apply it to random forest models because it leverages the decision tree structure of a random forest model. Well, I hope you liked the short introduction to forest Geiger clustering. If you want to have further information, please refer to the Read the Docs, where you can find more details on the algorithm. Thanks for listening.